Well, guys, so we were talking about in all my last four lectures about this simple harmonic motion. And today we are going to take up the case of simple pendulum. What is simple pendulum? You must have seen in the clocks, there are some clocks, they come with the pendulum. And pendulum is nothing but a metallic sphere. If you take one metallic sphere and just with a string, you hang it. So this is the metallic sphere of mass m, correct? And it is hanging with a string. And suppose length of the string is L. So in this position, it is basically the equilibrium position. At t is equal to 0, this bob is in the vertically hanging position. It is in this position only. And suppose if you want to make it have a simple harmony, what you have to do? You just push it. When you push it, it will move like this. Correct? It will go to some distance and then it will come back and it will not stop here. It will go further due to inertia and it will have new position as here, and then it will stop here and then it will go back again in the rightward direction. It will try to acquire a equilibrium position. So this is how this pendulum works. From its middle position, that is equilibrium position, it goes to and fro. This is called to and fro motion. But let us understand what is the mechanism behind it and why it is called a simple harmonic motion. As you know, in our earlier lectures, we have seen that these are the things we generally call oscillations. But every oscillation is not a simple harmonic motion. So let us see how this is a simple harmonic motion. So we will just, what we will do, we will just analyze the forces acting on this. It is having a mass, so naturally a downward force, gravitational force, will act on it, correct? And suppose at time is equal to t, position of the bob is like this, so angular displacement is theta, and this is the axis perpendicular to the board through which it is making an angular motion. Correct? Suppose this is a point A and this is basically the axis perpendicular to the board, you can assume. Now what is theta? Theta is basically angular displacement. Correct? So if you extend it, then this is also theta, and this force, that is gravitational force, this will have two components. One is like this, another one is perpendicular to the string, tangential to this motion, that is mg. This force will be basically mg sine theta, and of course Length of the string is L. So these are the two forces. If you resolve this gravitational force, it will experience. Now, in our last lecture, we have seen that for any angular displacement sort of thing, you must have a torque. So, where is the torque which is making this angular displacement? So, torque is, what is torque? Torque is nothing but R cross F. Means F, there is a force and there is a perpendicular distance to it. If you multiply those things, you will get the torque. So in this case, which is for mg cos theta component, there will not be any torque because it is in line with this string. But with this string, this mg sin theta is having a perpendicular direction. So torque will be mg sin theta into, of course, L. This is basically torque means this is moment. This is the moment. So it is making a moment of this magnitude. But what about the direction? Unless we specify its direction, it has got no meaning. So for specifying the direction, you just see Bob is moving in this direction, but your torque is in this direction, means it is towards the middle position. So basically this is minus mg sin theta into L. So this is the correct expression of torque which is acting on this with, of course, with the direction. Correct. So in our last lecture we have seen that our torque, this type of torque, which is pointing towards the middle position, and this is called, what is this called? Restoring force, restoring torque. Correct. So this is the restoring torque we have here, which is making the bob coming to the mid position like that. When it is at this extreme position, then also you will have this torque, direction of the torque will be like this. So this is how it is acting. Of course, at the middle position, theta is 0. When theta is 0, naturally this torque will be 0. But due to inertia, it moves in the forward direction. Now, in our last lectures, we have also seen that angular acceleration, that is angular acceleration, this must be proportional to minus omega theta. Correct? Or you can say this is equal to minus omega. So this is the condition of SHM. Correct? But in this case, if you see torque, in this case, if you see this torque is nothing but I into alpha. I alpha will be nothing but minus mg sin theta L. Correct? So, but alpha is nothing but mg I into L or sin theta. But if you compare these two equations, here alpha is proportional to minus theta, but here alpha is proportional to minus sin theta. So in this fashion, we can conclude that this is not a simple harmonic motion. This is not a simple harmonic motion. Correct? But for a small theta, we can write this equation as mgl upon I theta, because for small distances, sine theta will be nothing but we can assume this thing as theta. So for a small angular displacement, we can say that this is having a simple harmonic motion. I hope you are clear on this point. If you write this equation, then this is not a simple harmonic motion. But if you make some assumption for small angular displacements, then you can arrive at this equation, and this is basically nothing but your simple harmonic motion, because it is equivalent to this. So we can always write, if you compare these equations, equation number 2 and equation number 3, it is 1, this is 2, then what is basically omega square is nothing but mgl upon I, or omega if you like. What is omega basically? Omega is nothing but angular velocity. This we have seen in our last lectures. So this is omega. And what about here? If you see, m is given, g is okay, l is also length away. What about I moment of inertia. Moment of inertia for this bob along this axis, what will be that? Moment of inertia will be nothing but I will be ml square. If you put this value, then your omega will become mgl square upon ml square. Cancels out, then L cancels out, so that means it is basically G upon L. Correct? Angular velocity, you know what is angular velocity? Omega is nothing but 2 pi upon p. Correct? Then p is equal to 2 pi omega. If you put here, then what will be t? T means time period of this simple harmonic motion of this bob, means time taken in one cycle. So what will be that? That will be basically 2 pi root, of course it is omega is in the denominator, then this will be basically L upon G. Correct? And what is frequency? Frequency is nothing but 1 upon T. So you can easily write it as G upon L. So this is the expression we are getting from this derivation for the time period of this bob and for the frequency of the bob. Time period is nothing but time taken in one cycle, and here what is one cycle? One cycle is this. Suppose if it is in the middle position, it goes like this on the right side, it comes back, it goes to the extreme left, and then it comes back at the middle position. So this motion from this to this to this, again from the initial point from where it started. It is basically one cycle. So this is time taken in one cycle, and this is basically, of course, number of cycles per second. So this was all about simple pendulum, how the this torque is acted on this, how it is a restoring torque, what are the concepts behind, how it is simple harmonic motion, how it is not simple harmonic motion, what are the assumptions involved in this. So I hope this, with this lecture, the problem concepts behind the simple pendulum must be clear to you.